Hello and welcome to our video on voltage regulators. Today we're going to be discussing how these devices work and their applications in electrical power systems. Voltage regulators are devices that are used to maintain a constant voltage level in an electrical power system. They work by using feedback control to adjust the output voltage to match a predetermined set point. Voltage regulators can be found in a wide range of applications, from small electronic devices like smartphones and laptops, to larger systems like power grids. In fact, they're an essential component in many electronic devices and systems, as they help ensure that the devices operate within safe and efficient limits. In an electrical power system, voltage regulation refers to the process of maintaining a constant voltage level. This method uses feedback control to adjust the output voltage to match a predetermined set point. The following figure shows an ideal power supply where it provides a constant DC voltage despite changes to the input voltage or load conditions. An ideal power supply is a theoretical concept that represents a perfect power source with zero noise, perfect regulation, and no loss of power. It is important to note that an ideal power supply is a theoretical concept, and it is impossible to achieve in the real world. Real-world power supplies always have some level of internal resistance and noise, and are affected by changes in the circuit. The DC output voltage of a practical power supply changes under load as shown in the second plot. The output is also sensitive to input voltage changes, as shown in the graph figure. When the AC input voltage of a power supply changes, an electronic circuit called a regulator maintains a nearly constant output voltage. Line regulation can be defined as the percentage change in the output voltage for a given change in the input. Line regulation is a measure of how well a power supply is able to maintain the DC output voltage for a change in the AC input line voltage. The formula for line regulation is: line regulation is equal to change in V out divided by a change in V in. Multiply with 100%. Line regulation can also be expressed in terms of percent change in V out per volt change on the VIN, in units of percent per V as shown here. For example, a line regulation of 0.05% per V means that the output voltage changes 0.05% when the input voltage increases or decreases by 1 volt. Now, let us look at an example related to this topic. Let's say the data sheet for a certain 5-volt regulator shows that when the input changes from 7 volt to 25 volt, the output will change by no more than 100 millivolt. What is the maximum line regulation expressed as a percentage? First, apply the formula where delta V out is equal to 100 millivolts and delta V in is equal to 18 volt. After calculation, the line regulation as a percentage is 0.56%. Now, assume that the same data sheet shows that the typical change in output is 3 millivolt if the input changes from 7 to 25 volt. What is the typical line regulation? Applying the same formula, the line regulation percentage is equal to 0.017%. When the amount of current through a load changes due to a varying load resistance, the voltage regulator must maintain a nearly constant output voltage across the load. Load regulation is a measure of how well a power supply can maintain the DC output voltage between no load and full load with the input voltage constant. It can be expressed as a percentage change in load voltage. Load regulation can be defined as the percentage change in output voltage for a given change in load current. One way to express load regulation is as a percentage change in output voltage from no load, NL, to full load, FL, as shown in this formula. Alternately, the load regulation can be expressed as a percentage change in output voltage for each milliampere change in load current. For example, a load regulation of 0.01% per milliampere means that the output voltage changes 0.01% when the load current increases or decreases 1 milliampere. Sometimes power supply manufacturers specify the equivalent maximum error voltage instead of its load regulation as illustrated in the next slide. Commercial power supplies, such as you have in lab, have excellent line and load regulation specifications. The BK Precision 1651A is an example of a triple output supply, two 0 to 24 volt outputs and a fixed 5 volt output. Voltage regulation specifications for this power supply are: both line and load regulation has a value less than 0.01% plus 3 mV for main supply or equivalent to a maximum error voltage of 5 mV for a fixed 5 volt supply. Sometimes power supply manufacturers specify the equivalent output resistance of a power supply, Rout, instead of its load regulation. The Thevenin voltage is the voltage from the supply with no load, VNL, and the Thevenin resistance is the specified output resistance, Rout. With the load resistor in place, the output voltage is found by applying the voltage divider rule as follows. In terms of resistances, load regulation can be expressed as Rout over RFL times 100%. This equation is a useful way of finding the percent load regulation when the output resistance and minimum load resistance are specified. Let's try to solve the following example. A power supply has an output resistance of 25 milliohm and a full load current of 0.50 ampere to a 10 ohm load. First, what is the load regulation? And second, what is the no-load output voltage? The load regulation can be calculated by using the value of Rout and RFL, and the answer is 0.25%. Next, in order to calculate VNL, first find Vout by using Ohm's law. Vout is equal to 0.5 ampere times 10 ohm or 5 volt. Then VNL is equal to 5.013 volt. There are different types of voltage regulators, but the most common ones are linear voltage regulators and switching voltage regulators. In the linear regulator category, two general types are the series regulator and shunt regulators. The basic components of a series type of linear regulators is shown in this figure. And a basic op-amp series regulator is shown in this figure. The operation of the series regulator is illustrated as shown, where the control element maintains a constant output voltage by varying the collector-emitter voltage across the transistor. For example, when the output tries to decrease, because of a decrease in Vin, a proportional voltage decrease is applied to the op-amp's inverting input by the voltage divider. Since the Zener diode, D1, holds the other op-amp input at a nearly constant reference voltage, Vref, a small difference voltage or error voltage is developed across the op-amp's inputs. This difference voltage is amplified, and the op-amp's output voltage increases. This increase is applied to the base of Q1, causing the emitter voltage Vout to increase until the voltage to the inverting input again equals the reference, Zener, voltage. This action offsets the attempted decrease in output voltage, thus keeping it nearly constant. The power transistor, Q1, is usually used with a heat sink because it must handle all of the load current. Therefore, the regulated output voltage of the series regulator, neglecting the base emitter voltage of Q1, is given by this formula. From this analysis, you can see that the output voltage is determined by the Zener voltage and the resistors R2 and R3. It is relatively independent of the input voltage, and therefore, regulation is achieved, as long as the input voltage and load current are within specified limits. Now, let's try to solve this example. Based on this series regulator circuit, calculate the output voltage and power dissipated by Q1 if the load current is 200 mA. Firstly, finding the output voltage, using value of R2, R3, and Vref. From calculation, Vout is equal to 12.2 volt. Second, by using P equal to VI formula, we can calculate the power dissipated where the voltage change is 18-12.2 volt and current is 0.2 ampere. Multiplying both values will give the power value is equal to 1.16 watt. If an excessive amount of load current is drawn, the series pass transistor can be quickly damaged or destroyed. Most regulators use some type of excess current protection in the form of a current limiting mechanism. Current limiting prevents excessive load current. Q2 will conduct when the current through R4 develops 0.7 volt across Q2's VBE. This reduces base current to Q1, limiting the load current. Since the base-to-emitter voltage of Q2 cannot exceed approximately 0.7 volt, the voltage across R4 is held to this value, and the load current is limited to IL max is equal to 0.7 volt divided by R4. For example, a 1.4 ohm resistor will limit current to about 0.5 ampere. In the previous current limiting technique, the current is restricted to a maximum constant value. Fold-back current limiting is a method used particularly in high current regulators whereby the output current under overload conditions drops to a value well below the peak load current capability to prevent excessive power dissipation. Q2 conducts when VR5 plus VB equals VR4 and begins current limiting. VR5 is found by applying the voltage divider rule. An overload causes VR5 to drop because V out drops. This means that less current is needed to maintain conduction in Q2 and the load current drops. The advantage of this technique is that the regulator is allowed to operate with peak load current up to IL max, but when the output becomes higher than this because of loading or a short circuit, the current drops to a lower value to prevent overheating of the series transistor, Q1. This method also helps limit the size of the heat sink required to protect the transistor. The second basic type of linear voltage regulator is the shunt regulator. As you have learned, the control element in the series regulator is the series pass transistor. In the shunt regulator, the control element is a transistor in parallel, shunt, with the load. The basic components are shown in the block diagram in this figure. In the basic op-amp shunt regulator with load resistor in this figure. The control element maintains a constant output voltage by varying the collector current in the transistor. A resistor, R1, is in series with the load. The operation of the circuit is similar to that of the series regulator, except that regulation is achieved by controlling the current through the parallel transistor Q1. Shunt regulators use a parallel transistor for the control element. If the output voltage changes, the op-amp senses the change and corrects the bias on Q1 to follow. For example, a decrease in output voltage causes a decrease in VB and an increase in VC. Although it is less efficient than the series regulator, the shunt regulator has inherent short-circuit protection. The maximum current when the output is shorted is V and divided by R1. The two types of linear regulators, series and shunt, have control elements, transistors, that are conducting all the time, with the amount of conduction varied as demanded by changes in the output voltage or current. The switching regulator is different because the control element operates as a switch. All switching regulators control the output voltage by rapidly switching the input voltage on and off with a duty cycle that depends on the load. Because they use high-frequency switching, they tend to be electrically noisy. The on and off intervals of Q1 are shown in the waveform of shown figure. The control voltage swings below and above the threshold voltage, off and on states. The capacitor charges during the on time, T on, and discharges during the off time, T off. When the on time is increased relative to the off time, the capacitor charges more, thus increasing the output voltage, as indicated in following figure. An increase in the duty cycle increases the output voltage. When the on time is decreased relative to the off time, the capacitor discharges more, thus decreasing the output voltage, as in figure. A decrease in the duty cycle decreases the output voltage. In the step-down configuration, also called a buck converter, the output voltage is always less than the input voltage. A step-down switching regulator controls the output voltage by controlling the duty cycle to a series transistor. The duty cycle changes depending on the load requirement. Figure shows a basic step-down switching regulator using an E-MOSFET switching transistor. MOSFET transistors can switch faster than BJTs and have become the preferred type of switching device, provided that the off-state voltage is not too high. Because the transistor is either on or off on all switching regulators, the power dissipated in the transistor is very small and the regulator is very efficient. The pulses are smoothed by an LC filter. When the transistor is on, C charges. And L opposes the change in current. When the transistor is off, C discharges and the polarity of L reverses, helping to smooth the output DC. A basic step-up type of switching regulator, sometimes called a boost converter, is shown in figure, where transistor Q1 operates as a switch to ground. In a step-up switching regulator, the control element operates as a rapidly pulsing switch to ground. The switch on and off times are controlled by the output voltage. Step-up action is due to the fact the inductor changes polarity during switching and adds to Vin. Thus, the output voltage is larger than the input voltage. When the transistor is on, the field builds around L, and C discharges. When the transistor is off, the field collapses from L, and C charges. This regulating action maintains V out at an essentially constant level. A third type of switching regulator produces an output voltage that is opposite in polarity to the input. A basic inverting switching regulator is shown in figure. This is sometimes called a buck-boost converter. Inversion occurs because the inductor reverses polarity when the diode conducts, charging the capacitor with the opposite polarity of the input. Initially, when the pulse goes high, it turns on Q1 and biases D1 off. The voltage across L drops as the field builds. When the pulse goes low, Q1 is turned off and D1 is biased on. This charges C with a negative charge. The LC filter smooths the rapid charging and discharging. As with the step-up regulator, the less time Q1 is on, the greater the output voltage is, and vice versa. Several types of both linear and switching regulators are available in integrated circuit (IC) form. Generally, the linear regulators are three-terminal devices that provide either positive or negative output voltages that can be either fixed or adjustable. In this section, typical linear and switching IC regulators are introduced. The popular three-terminal regulators are often used on separate PC boards within a system because they are inexpensive and avoid problems associated with large power distribution systems, such as noise pickup. The 78XX series is a fixed positive output regulator available in various packages and with standard voltage outputs. Other available output voltages are given in 78XX regulators table. The only external components required with the 78XX series are input and output capacitors and some form of heat sink. These ICs include thermal shutdown protection and internal current limiting. The three terminals are input, output, and ground as indicated in the standard fixed voltage configuration in shown figure. The 78XX series are primarily used for fixed output voltages, but with additional components, they can be set up for variable voltages or currents. The 79XX series is typical of three-terminal IC regulators that provide a fixed negative output voltage. The 79XX series is the negative output counterpart to the 78XX series, however the pin assignments are different on this series. Other specifications are basically the same. Figure shown indicates the standard configuration and part numbers with corresponding output voltages that are available. The LM317 is an example of a three-terminal positive regulator with an adjustable output voltage. There is a fixed reference voltage of plus 1.25 volt between the output and adjustment terminals. There is no ground pin. The output voltage is calculated by V out is expressed by the following equation. The standard configuration is shown in figure. The capacitors are for decoupling and do not affect the DC operation. Notice that there is an input, an output, and an adjustment terminal. The external fixed resistor R1 and the external variable resistor R2 provide the output voltage adjustment. Based on the following figure, what is the value of V out? The output voltage is calculated by using the formula, and the answer is 16.8 volt. As you know, an IC voltage regulator is capable of delivering only a certain amount of output current to a load. For example, the 78XX series regulators can handle a peak output current of 1.3 ampere, more under certain conditions. If the load current exceeds the maximum allowable value, there will be thermal overload and the regulator will shut down. A thermal overload condition means that there is excessive power dissipation inside the device. IC regulators are limited to a maximum allowable current before shutting down. The circuit shown is uses an external pass transistor to increase the maximum available load current. The value of the external current sensing resistor, REXT, determines the value of current at which QEXT begins to conduct because it sets the base-to-emitter voltage of the transistor. REXT sets the point where QEXT begins to conduct. REXT is determined by the following formula, where Imax is the highest current that the voltage regulator is to handle internally. For example, if Imax is 1 ampere, REXT is equal to 0.7 ohm. What minimum power rating is required for REXT? P is I squared R, and the minimum power rating is equal to 0.7 watt. The 78S40 is an IC containing all of the elements needed to configure a switching regulator, using a few external parts. It is a universal switching regulator subsystem because it can be configured as a step-down, step-up, or inverting regulator by the user. The data sheet shows typical circuits for these configurations. By using a proper circuit connection, this universal regulator can be configured to different type of regulator. Here is an example of circuit connection used to configure 78S40 as a step-down configuration, and that's a basic overview of how voltage regulators work. I hope you have a better understanding of the role these devices play in maintaining a stable voltage level in electrical power systems. Thanks for watching.